Okay, so gentlemen, thank you for tuning in, for the trust and the confidence to participate in this course, which is the Infralab course. We call it the Infralab course because we felt that for you to be an infrastructure expert, we need to integrate the three nexus, which is water, stormwater, sewer, and road, and then come to a infrastructure expert. So this is the material we'll be using. This is module 1. Module 1 is water reticulation system. So we're going to study about how to do water reticulation system in the first 3 weeks. Okay, so I'm seeing somebody raising his hands. I'm wondering why you're raising your hands. Okay, so what's the why, sir? Can you say something?
I can see your screen, please.
Okay, I think it should be from your own end.
I also cannot see your screen. Okay, it's visible now.
Okay.
Yeah, I can see it now.
Okay, so I go back to recording again. Okay, recording is not paused, it's there. Okay, so you will see some tests. So let me just explain some of the materials here so that you know what you have on ground. So you have what I call nomogram. Nomogram is for pipe sizing. So I have provided 3 nomograms, one for PV material, one for wrought iron, for iron material and steel material, the other one for concrete material and asbestos. Then here you have what I call water quality requirements. Then we have some EPANET exercises. We have the EPANET manual. This manual is for you to, it's for futuristic use. I'm not going to open it, but it's for you to, if you want to go for into studying about EPANET, you can do that. There's a whole lot you can do with it. Then we now have the tests for the course, which is from chapter 1. You can see a PDF material from chapter 1, which is introduction to chapter 9. Then you have what I call ABC design or branch system. These are exercises we're going to do. Then you have the EPANET software as well, which is already in a folder. Okay, so now let us go to chapter 1. Let us read the text. Okay, like I said, I will try as much as possible and be very fast about it because this can be sometimes, in my opinion, it can be boring. Okay, it can be boring because it's something that some of us already know, while it's for some other people it's something new. But whether it's new or something you already know, it's good that we don't waste too much time on them because we quite have a lot to cover. Okay, so this is water supply, water demand, supply, and distribution. So in other words, you have to take care of what's the demand and how do you get the supply, and then how do you distribute. Okay, so our key objective is to understand the fundamental structure of centralized water supply design. It is centralized, it can also be decentralized. We'll still come to that. Yeah, it's just a question of putting it in phases, become decentralized. Okay, and also for us to understand the hydraulic system of a centralized water supply system. And then let us understand the functions and the structure of the single elements. What are they for? Then we also should be able to have the ability to plan, design, and calculate centralized water supply system and its elements. So these are the objectives of this training. So this is just a picture to reflect water. On your left, you have a water in the glass cup. On the right, you have upper right, you have a well. Then on the down, you have an intake structure of a dam. Okay, so what you could see here is just to bring you up to speed. This is an example of the one on my left is a reservoir. And from what I'm seeing, it seems to be an underground reservoir. So reservoirs can be underground, they can be surface, and they can be elevated. So this is a typical underground reservoir because you lack space in the surface, and maybe there's space constraints or there are railway up at the surface or something, you need to go underground. But then you need to make sure you do it the right way. On the left, you have your pumping station. Wherever you have more than two pumps, you can refer that place to as pumping station. Pumping station can be booster station, it can be upper lift pumps, and what have you. Then what you have again is what we call the aerator. I should have been asking all this question, but I don't want to go that route. We don't have that time. This is a typical aerator used in the water treatment plant. What the aerator does is to aerate the water, because the basic methodology of treating water is to aerate it, to introduce oxygen. What does oxygen do? The major mineral element in water, okay, is iron. Most times is iron or silica, or a mixture. It's a combination of iron and so on other mineral elements. So basically, they come in form of iron 2. So when you aerate them, they move from iron 2 to iron 3, 2 plus to 3 plus. So 2 plus, which is iron 2, is normally insoluble, soluble in water. But iron 3 is insoluble in water, or partially soluble, whatever. Okay. So when you aerate water, the first thing that happens is that iron 2 converts, gets oxygen, which is O plus, and comes to iron 3. Then with iron 3, you can see it becomes turbid, it becomes suspended, sort of. Then if you put a flocculant, the appropriate one, which is always calcium carbonate, calcium hydroxide, it coagulates. And when it coagulates, it forms lumps. Then you can easily use filter system. Either use sand filter, use membrane filter, or whatever filter system you have that's cheaper for you, that's accessible, that is feasible. You now separate the suspended solids. So that's why most times when you look at water, so surface water, they are turbid, okay? They are looking, brownish and what have you. But as soon as you aerate them, you see them percolating. Once they get the oxygen, they become massive, sort of, and then they settle underground. So it's either you flush them through a bottom outlet, or you further put in coagulants. And when you put those coagulants, they flocculate, sorry. And when they flocculate, you can easily filter them. And like I said, the basic filtering system is sound filters, which can be rapid or slow sound filters. Then on your right, what you have there is a bed, is a sedimentation bed, filtration bed. Okay, you call it sedimentation bed, but it's also a filtration bed because there are filter elements in there. And those filter elements are basically sand. So that is that. Then this is a typical, I hope this thing is recording. Yes. Yes. So this is a typical schematic diagram of a centralized water supply system with its 5 key elements. Okay. The 5 key elements is the collection system, the transport system, the storage system, and the distribution system. So in the collection system, that is the water source, as you can see there. So basically, you start with the raw water intake. Okay. Then from the raw water intake, you go to the transportation system, which is now the transmission pipeline. So depending on the type of water, the source of water, okay, of course, we have based on their order of priority, or based on the order of economic extraction method, you have spring. Spring is the best. After spring, you have groundwater. After groundwater, you have surface water. After surface water, you have rainwater. These are after surface water, after groundwater, you have water from long distance water supply. Yes, water from long distance water supply. Then after long distance water supply, you get your surface water. After your surface water, you get your rainwater. These are the order of water in terms of their purity, ease of extractions, and economic viability. So depending whether the water needs further treatment, you develop a treatment plant. Then from treatment plant, you transmit the water. When you transmit the water, it's ideal for you to have a service reservoir. The service reservoir serves many purposes. Most times for further treatment, most times to serve as a buffer or as a pressure regulator. Okay? If water coming from transmission to distribution sometimes can come with very high pressure that can really cause domestic local problems. So most times you have a service reservoir where you can further treat or you regulate the pressure to the end user. And then from there, it goes to your distribution network, which is where we're going to focus mainly on, okay? Majorly because that's where the issue, that's where engineers have issues. Then from the distribution, you design distribution based on peak hourly flow. While you design the transmission, the treatment plant on daily maximum flow. I will still come to all those ones. But just take note that the distribution system is designed based on hourly flow, while the transmission and the treatment plant is designed based on daily requirements. Okay, these are the basic requirements you need for water. Because sometimes when we say each person needs 100 or 150 or 80 or 60 liters per person per day or per capita per day, you'll be wondering, how did you arrive at this? Well, this is just an example of how to arrive at this, okay? The average human being need about 3 to 10 liters of water for drinking in a day. Get the point? And then for food, for drinking, for preparing food, washing dishes, and all of these things, you need about 15 to 25 liters, right? Then flushing toilets, irrigation, gardening, swimming pool, car washing, you need about 50 to 60. Then other things, which is agriculture, public, commercial, and everything, also have their own requirements. Now, these things come in range. They are not static. They depend on standard of living, okay? Take, for instance, those of us who are living in the cities, you have flush toilets. The average flush toilet in the past used to use about 8 liters of water to flush. But based on technology, you can see flushing requiring about 4 or 5 liters, averagely 6 liters these days. You go to your showers all over the Western world, their showers are now you have motion sensors, okay? That once you want to shower, you press the button, the shower runs for like 5 seconds. If you don't flush it again, it will not come again. All these things are water saving mechanism, kind of water saving models. So, but despite all this, on the average, one needs about between 100 to 150 liters per day to survive. This is not too necessary, but this shows you the importance of water, clean water. Okay, clean water to human health. Okay, this study shows that in Germany, the decrease in death rates as a result of more water treatment, more improvement in water sanitation, water and sanitation exercise. So what we're saying in essence is that working on good water improves lives. Okay, so there are basically three impurities found in water, okay, that had significance. Microorganisms, chemicals, and then physical. When you treat water for 3 parameters. You treat it for biological contamination, you treat it for chemical contamination, and you treat it for physical contamination. Okay, the microorganism is basically the E. coli, the various fungi they can find in water. The chemical constituent is so much: manganese, fluoride, copper, iron, and so many of them. We're going to go through them. Then the physical ones has to do with conductivity, pH, and turbidity. So these are just some of the things you need to treat water for. Okay, so these things is something we can read. When we read them, we understand them. Okay, so I think that is all for the introduction. If there's no question, we'll quickly go to chapter 2. Any question on this? No, there shouldn't be any question. I think it's very quite self-explanatory. So we go to chapter 2. So here, once again, we will see the design again. So chapter 2 talks about collection, overview of water sources. So I've already said this in passing. In the source of water, you can have the long distance water supply. Like in Abuja, those of us in Abuja, you know that if you're living in phase 1 of Abuja, the water we are using is coming from Buhari. So let's assume I'm building an estate in Lugbe or in Kuje, and I need water from Buhari. It means I'll just take my water from Buhari as a direct source and then store it in my storage reservoir. Okay, good. Then, if that is not available, we can have surface water. Surface water can come in 5 different forms. The first one can be rainwater. Number 2, it can be treated sewage. Yes, some countries now treat their sewage. They don't use it for drinking purpose, but they use it for that irrigation, another form of water usage. Then the surface water can come in form of sea. All of us know the challenge that comes with sea water. We're talking about salty water salination. And then we can come in form of river water. Also has its own challenge. It can come in form of lake. I remember Stuttgart's Baden-Württemberg in Germany. Their lake is located where they call Lake Constance in southern Germany, well protected. Okay, so they use lake water. That's their water source. Then it can also come in form of barrage water. Those ones you can see them in Netherlands, in Netherlands, in Amsterdam and Rotterdam. Then whichever source it comes, the surface water, they will require an intake structure. So when you're talking about surface water, the first thing you talk about is your intake. It must have an intake structure. Whether it's a treated sewage, is a water sewage, even rainwater, it requires an intake. Then from the intake, it goes to the treatment plants. Then from the treatment plants, it goes to the storage and distribution. Okay. Then it also can come in form of groundwater. However, groundwater can come in 2 forms also. It can come in form of recharged groundwater. It can also come in form of natural groundwater. So when it comes in form of recharged groundwater, you need to have bank infiltration water. This is one technology that we have left, which we need to go back, especially already gone back, especially in arid regions where they have water issues. The idea is that because there's no groundwater, you go close to the stream, close to the river, at a distance that will provide you enough buffer. You dig a well, knowing fully well that well will require the river to recharge. Okay? I mean, this is what they do mostly in Egypt, countries like Egypt, where 99% of Egypt's water requirement comes from the Nile. Yes, you heard me well. 99% of the water they require in Egypt comes from the Nile. So you see a lot of this kind of bank infiltrated water. You see them digging wells here and there. But what is discharging it is the Nile. So all they need to do is to create diversion channels. As the Nile is coming, you see more than 1,000 diversion channels going into the cities, even their irrigation, their irrigation systems. This is what they do. Little wonder they wanted to go to war with Ethiopia over the building of the hydropower systems along the Nile. Then the next one is the one we all enjoy in Nigeria, and that is the natural groundwater. You just go in there, dig the water, and some places in the southwest, they have a lot of spring water. I know of that one, including Warm Spring. So irrespective of how it comes, for the groundwater, you need to, for the bank infiltration well, you have what they call the tube well. Like I said, it's not much in the southern Nigeria, but in the north Nigeria, this is something they have to go into, which are already doing, tube wells. Then they also can have horizontal filter well, okay? And then they can also have infiltration galleries. I'll show us pictures of all these things. Then if it is natural groundwater, we all know that one. You dug your well. If it's spring water, you find a mechanism to tap the spring. But all of them will still go to treatment. And from treatment, they go to distribution and this thing. When you are selecting your water source, you don't just select water source arbitrarily. You must consider 5 key factors. The number 1 factor is the quality. Quality is key. Surface water is the least in quality and is not sustainable in most of the time. The most sustainable source of water is the spring water. But spring can be last. Spring, or what we call artisan well. Artisan well is a spring water or artisan well because the pressure of the water is on the surface. That's just the meaning. The pressure of the water is on the surface. Normal well that we dug, the pressure of the water can be 100 meters below, 50 meters below, 20 meters below, 3 meters below, depending on where you are. So you definitely need some level of pumping. You need a pumping to pump it out, which is energy. But in case of artisan well or spring, you don't need energy because the pressure is already on the surface. So all you need to do is to build diversion channels, extraction channels, and then you take your water. So it means that surface water should be your list in consideration because of the high cost of treatment. In most cases, it requires a treatment plant, whether large-scale treatment or small-scale treatment. Most times, groundwater don't require treatment, but sometimes they might require minimal treatment such as aeration, except where there are issues of subsurface contamination like lead, arsenic, okay, because of mining activities close by, or issues, or just the geography of the area makes it susceptible to chemical contamination. All right. Then the second consideration you must consider is the quantity. You must consider the quantity. Who are you servicing? Does the quantity meet? If I'm to use groundwater, no problem. But how many groundwater do I need? What is the sustainability of that groundwater? What is the level of recharge? I need to do some pumping tests. I need to determine if the level of extraction and level of recharge is the same, or is the recharge is more. Okay, and that comes to do pumping testing, do your drawdown, so that you know, and it also helps you to know what kind of pump to use, so that your level of extraction does not undermine the recharge. Then the next factor to consider is the economics. What is the economic of getting this water? It's one thing for me to locate my well 1 kilometer, 2 kilometers away, but then I need to consider the transmission. I need to consider what kind of pump I will use to transmit that water, and the energy requirement, how do I trade it off? Then the last one is safeguard of supply. You don't source water from anywhere. It's a challenge we're facing in Abuja now. So we have this dam we call Lower Usman Dam in Abuja, located somewhere in Papi. As we speak now, development is catching up with that dam. We're beginning to see human activities around the dam, open defecations and a whole lot of things happening around the dam. That if that dam is not safeguarded, development will catch up with it. That's why in big cities, they will put a buffer around their water source. Sometimes it can be 1 kilometer radius. Nobody does farming, even farming. Because when you allow farmers to be around the water source, those of them who are using NPK fertilizers, you begin to see a lot of nitrogenation of your water. And you know what nitrogenation of water means? It means to growth of algae, and some of these algae can be very dangerous. Yes, it can be stubborn, it can be dangerous to the body. So you begin to see a lot of greening because you are supplying nitrogen, and nitrogen and spirogyras and algae, they love nitrogen, and these nitrogen bacteria. So you need to take care of your safeguard. It's very, very important. So the next thing is to look at the preferences in choice, which I've already explained. Spring, groundwater, surface water, okay, which one is better and how to take care of them. For the groundwater, you need to look at the formation. We know all these things when we come to drill boreholes. You look at the multiple aquifers. Sometimes the first aquifer is not the best aquifer for many factors, okay? So you need to consider the hydraulic head. You need to consider the porosity. You need to consider the average pore sizes. So these are things you need to look into, you need to consider before you establish your groundwater parameters. So this is something about groundwater. I don't want to go into all this. It's about the Darcy laws that controls groundwater hydraulics, okay? The velocity of flow is directly proportional to the head and inversely proportional to the distance. So this is a typical formula for groundwater. And you can read this and understand. We're engineers. Okay, so just a physical demonstration of aquifer. So we have what we call confined aquifer or unconfined aquifer. Unconfined aquifer are aquifers that don't have any level of confinement, like you see here. So basically, it's from recharge water and then from water from closed streams. But the confined aquifers have some confining membrane. Okay, these are like deep aquifers. I remember when we were kids, they used to tell us that there's a river flowing inside the ground, all those theory. It's simply talking about the unconfined aquifer in the ground. So most times, if you want to get a sustainable water that will last for a long time, then you need to look for that river in quotes. You need to look for the river in the ground, which is simply, you need to look for the confined aquifer. Okay, and that's why sometimes you need to drill, you need to overcome some level of overburden. Okay, overcome some level of overburden. Maybe sometimes also overcome some confining strata before you now approach the real aquifer, which most of the time is more sustainable, though you will require a lot of energy to pump them out. Sorry, you might not see this very well, but when you read it through, it's simply trying to tell you the component, the characteristic of well. So you have your submersible pump at the end, which is your motor. Then you have your screen, your inlet. Okay, you have your filter pipe, you have the diameter of the borehole, you have your pressure pipe. These pressure pipe are very key, gentlemen. Please, the pressure pipe of a borehole starting from 60 meters should be minimum of 10 bars. As you are going down, you should be increasing the pressure of the pipe. This is what kills a lot of boreholes. Ideally, you should go for 12 or 14 bars, because as you are going deep in the ground, you need a strong pipe, a pipe that can withstand that level of pressure. Okay, then here you have your gravel filter, you have your barrier pipes. This is just for you to understand. Then finally, you have your wellhead, then you have your ventilation. Can somebody tell me why you need a ventilation in a well? Can somebody tell me why you need to ventilate a well? How many of us have pumped water from a well and it has some odor? That is iron. So as soon as it comes on the surface and is well aerated, you won't see that odor again. So if you close a well and you didn't give it space, then it means the iron too will remain in solution comfortably, and they give out odor. And then there will be anaerobic activities, whereas we need aerobic activities. So anaerobic activity normally generate odor, because anaerobism is the absence of oxygen. And when you look at absence of oxygen, most times hydrogen is working. And when hydrogen reacts with sulfur, all of us know about hydrogen sulfide. Or when the hydrogen reacts with nitrogen, all of us know about ammonia. If you remember your chemistry, ammonia and hydrogen sulfide, they don't give you pleasant odors. So I want you to take note of that. And this is why in most anaerobic activities, you begin to have those odors, because it's not like you're producing ammonia, okay, and its varieties, okay, or you're producing sulfur and its varieties. And by the way, some of these bacteria, microorganisms, they are lovers of nitrogen and sulfur. They love it so much. Okay, so this is an example of a horizontal filter well. Okay, you can see. Okay, these are old technologies, but I can tell you they are still very functional these days. Let me tell us my experience as somebody who travels often on the international scene. In fact, this year I've been to Germany twice anyway, attending conferences and exhibitions. Something like also organized for engineers. One thing I have discovered is that the technology we need has to come from us. Because in the Western world, some of them have gone beyond the technology of yesterday. So they cannot go back and do research on the technology we need, especially in some of our rural areas. Okay? I mean, here you see them using washing machine, using showers, or I don't know the technology I'll talk about, or let's say well, or let's say solar powered well, for instance. If you go in the Western world, you won't see all those things. Why? Because they have a functioning electricity grid. They have energy, a sustainable energy power. So what are they doing with solar power boreholes? But here, we don't have it. So we all just have to resort to some solar infused technology, both in our irrigation. In the irrigation systems, they have sprinklers. They have, high level, they have drip irrigation. Drip irrigation pipes. Drip irrigation, you know what it does? It saves water. It's so precise. Okay, it's so effective. But here, we don't have money to buy pipes. Even when you buy those pipes, you are taking more water from the open stream. There's the issue of blockage. that's going to go on. So there are a whole lot of factors. So when you see technologies like this, you shouldn't jettison them. They are still very, 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 very much effective. This is a typical well. I don't see anything about having a well. As long as you have a good filtration system and it's far away from contamination, because the ground will naturally filter them and then you can pump them out using whatever pump you can use. Then, so these are some of the things we're just doing today. So this place is just trying to tell you how spring water develops. Sometimes you see rain falling at a distance, and then over time, it builds pressure. And then any small features on the ground, the water will come out as under pressure, and that becomes your artisan well. So these are in form of, when we study some of these things, these are pictorial things just to demonstrate some way we can tap spring water, groundwater, and surface water. Okay, so this is another one. This is another one. In fact, we're planning to implement this one somewhere in Imo State, where Abia State, sorry, where they have issue of groundwater. So we're thinking of digging a well close to the stream and then building a pipe from the stream, okay? So that when the stream is working, water will enter here, this pipe is perforated, then it will filter and then come to this well. Then from this well, we'll put in a pump, and then the pump will pump it out. But then you must find a way and make sure you protect the banks, the bank of the river, so that erosion and wearing will not take them off. This one is a typical intake of a dam, okay? So here you have the bridge where you can climb, and then this is your intake, perforated also. This intake can be one or can be two. And then you have this spring. This thing is meant to take it down or up, depending on the water level. So when the water level is down, you can take it down. So from here, it will filter. You know why this filtering system is important? Because there are a lot of things, activities happening here. There are a lot of debris, falling trees, falling leaves, stones, dead fishes, dead animals, and what have you. So this pipe will serve as a kind of filtration membrane that will now allow it to filter. Then from here, it goes to further treatment, which basically is going to be erosion or any other minimal treatment that might be required. Okay, the same thing goes to this one. So you can also see this is surface water. This is the intake structure to help filter. Then from filtering, it comes to this well. From this well, you can pump it out or it can continue to flow. So this is an example of a river intake structure. Okay, this is this is how the river intake structure serves. So this is the river here. This is the highest water level, lower water level, medium water level, and high water level. So here you see your intake structure. So your intake, which is basically a perforated pipe, and you can see that this intake structure, to allow the wave of water not to carry it away, you pin it to the ground. Gentlemen, you know what I'm talking about. More like a pilot. You pile it into the ground so that when water comes in, and then from here you pump the water out. So this is a ladder this is a riser, sorry, for you to be able to go in here and clean it once in a while. You clean it once in a while, okay? So when water comes in, you can still cover all these risers, okay? Of course, it's going to be steel element you use for the risers. And then this also helps you to monitor the water level. So the water level can be here. When the stream level is here, the water level can come up to this place. And then this is also a manhole. You can build a second manhole so that when the water level is higher, you don't need to climb through this riser. Rather, you move in through this other riser. So this is just a typical treatment plant. Water intake structure. So it must have a backwash pipe. This is very, very important. In fact, every pumping station must have a backwash so that once in a while you can backwash the debris, the sediments, either sand sediment or what do you call it again? Dissolved sediments, biological sediment. TDS. Okay. All right. So that is that. So just in case you want to follow the line of using rainwater, that is how to go about it. Okay, so rainwater, I don't want to go into rainwater, but I think rainwater is something we have to start looking at somehow. Basically, I think the rainwater system need to have a collector, have a kind of a swings funnel, have a hanging funnel. Okay, during the first flush, okay, first flush is the dirty one for sort of rain, or after a long period of long rain, you need to have a way and make sure that that first flush does not enter your system, and other things you can do. Then you have the baffle tank. Okay, the baffle tank basically is for you to be able to sieve your rainwater and then make sure the sediment accumulates separately. Then the decanted water, which is surface water, will now flow through your tank. So you have to provide some level of buffer, baffle tank. So I think we don't need to waste our time in all this. We can just go through them, and then I think they are self-explanatory, and we can really discuss them. So these are like artificial recharge of water. This is what they do in arid region like Morocco, Tunisia, in Saudi Arabia. This is not for Nigeria. We have enough water. This is where you pump water from the sea and recharge the groundwater in the desert. Okay, then you have a man-made river like Gaddafi tried to do, or he did. You know, you use it so that by the time you recharge it, but the problem is that after a while you have salt accumulation, and can be difficult to treat most times. Okay, so that is the end of chapter 2. I hope no question. Sorry, I warned us at the beginning that this section can be boring for some of us, because most of us, so just yesterday we registered for this course. This course was supposed to start 2 weeks ago. We didn't start because we had only like 6-7 people registered, but it's good to know that we have more than 15 this class now, or close to that number. Okay, so chapter 3, back again. So chapter 3, we're talking about this time around, we're talking about definition, some terms. Let us discuss some terms. Let me at this point also say that some terms can be used interchangeably. One of the things that will make you a water expert is the ability to use the terms very, very well. So we have water consumption. What is water consumption? It says a provided area, actually delivered and measured water quantity. What is water demand? Water demand is estimation of the water qualities to be delivered in an area of supply based on planning and design of your water supply systems. Water demand calculation, it says a forecast. It's a forecast of the water requirement. Okay, so we've done about this before. All this one that we can read and understand, I'm going to flip them because I want to go into the real thing. So these are things that can influence water consumption. So when you make assumptions, even though we have national standards, but at the same time, it's good for you to know what can influence your water consumption. Living standard can influence water consumption. The higher the living standard, the higher the water consumption. That is straight up. Then climate change can be a factor. Then the type of water supply and disposal can also be a factor. The further away the water source, the less water consumption you have. Then industries can consume quite a lot of water. Then you have the water tariff. Water tariff. If the billing and the water tariff is high, people will manage how they use water. That is known. If the water quality is poor, less use of water. If the pressure is poor, less use of water. If you create the right environmental awareness, there will be more use of water. Then technical progress. So we're looking at, we have discussed this before. We said this is like something that gives you influence. So the higher the distance of water, the less consumption people consume water. Okay, so this is what we call water consumption. So based on time of the year, okay, northern Germany and southern Germany. It can also be northern Nigeria, southern Nigeria. So water consumption is different depending on the period of the year. All of us know that during the hot season, water consumption goes high. Then during the rainy season, water consumption goes low. During cold, during harmattan. Okay, so this is also what we call in a 24 hours stretch based on rural area. The blue one is rural area, the green one is small town, and the red one is big town. So if you look at the red line, not the horizontal one, you find out that the water consumption is almost uniform. So irrespective of whether in the morning, from 0 to 24 means 24 hours in a day. One obvious thing you need to observe here is that from 0 to 6, this is when people are sleeping. Water consumption is usually low. Then from 5, 6 o'clock, especially in the rural areas, people are ready to go to farm. People wake up from sleep. Everybody's brushing, everybody's going to toilet, everybody's drinking, everybody's cooking, everybody's washing. There's a lot of activities. So the water demand picks up. That's what we call peak period. Then at 9 o'clock to 12 o'clock, nothing much is happening. It goes back to almost where it was before. But then when they are coming back from farm, which is around 12 o'clock, 2 o'clock, you discover that everybody is coming back to drink water, to wash, to bathe, and then the water demand picks up again. So this is just to demonstrate to you about what we call daily consumption pattern. We call it consumption pattern. And when you are doing your design, you must factor in the peak periods. It's for those who are engineers, which are going to do road design towards the end of the lecture. You find out that when you want to do a road, you need to consider the frequency, the peak period of the car. You start counting the number of cars flying that road. That's the period of okay. So forecasting water demand or demand calculation. In water demand calculation, forecasting, you forecast for the worst case scenario. That's just the whole thing I want to say. So you design period must be well forecasted. Are you designing for 20 years time? Are you designing for 30 years time? It is the value of that period that you use in your design. You don't do a design and use the values of today. That's why you need to have your design horizon. You need to have, say, I'm designing for 30 years. I'm designing for 50 years. I'm designing for the next 20 years. Or I'm designing for the next 100 years. 100 years is too much. Forget about it. Nobody's going to. And besides, who told you that in 100 years' time, that development would not have overstretch your design? So typically, people design for 25 years or 50 years. But remember, factor of safety is something that you need to be careful. It's something that you need to be careful. You need to use it, because the higher the factor, safety factor, the higher your values, the higher your summary, and the higher your cost. Okay, so you say the goal is to determine the most correct design peak flow for all parts of the water supply system. You must design the peak flow. You use the peak flow at the peak periods, your design. Okay, so these are some things you take into consideration. What is the current state, and then what is the forecasted development? Okay, and this is very, very important. So these are some of the parameters you'll be seeing. We'll be talking about average specific daily demand. The unit is liters per capita per day, or liters per unit per day. Then we have the maximum specific daily demand. To move from daily demand to yearly demand to specific demand, you simply multiply by a factor of safety, FD. And that fact, we have two types of factor of safety: daily factor of safety and hourly factor of safety. The daily factor of safety is for you to design daily parameters, and the hourly factor of safety is for you to design hourly parameters. You come to see all these things, but I want us to get used to them. They are units. So in discussing factor of safety, now, the higher the population equivalent, the higher the population of equivalent you are designing for, the lower your factor of safety. So it's inversely proportional. If I'm designing for 1,000 people, it's different when I'm designing for 1 million people. If I'm designing for 10,000 people, sorry, let me start with 10,000. The factor of safety I will use will be higher if I'm designing for 1,000 people. Let me say it again. If you are doing design for 10,000 inhabitants, I might be using a factor of safety of, let's say, 1.5. But if I'm designing for 1 million people, I might be using a factor of safety of 1.2. The reason is that as a higher number, those who are into modeling, the more the sample group, the less the internal error. The higher the sample group, the errors will cancel out. But the smaller the group, the error or the average mean will be skewed. That's why in most times if you are doing modeling or you are doing sampling in science, the larger the group, the sample group, the better. The higher the sample group, the better for you, because it gives you the variability is positive. Let me use that word. You can cancel out. This person can be 100 years old. This person will be 70 years old. None of the two will come together. But if you have many 100 years and many 50 years, the mean, I don't know how they say it. I'm not a statistician, but something revolves around something, which I've forgotten, by the way. Okay, so here you see that the more, these are sub-factor of safety. This is hourly factor of safety. This is maximum factor of safety, and this is the hourly daily. So you can see that if I'm designing for 1,000 household or 500 housing units, my factor of safety goes to 0.008. Whereas if I'm designing for, let's say, 10, it goes to 0.009 across board. So just take note of that. What is the essence of this? So here again, if you, this is hourly factor of safety, and this is daily factor of safety. So you can see that if I'm designing for 1 million inhabitants, my hourly factor of safety is 1.77, while my daily factor of safety is 1.38. Whereas if I'm designing for 100 inhabitants or 100 population equivalent, that's the technical keyword, population equivalent, my hourly factor of safety will be around 5.6, while my daily factor of safety will be 2.3. So the whole thing now is just for you to see the movement, that as this one is moving down in increasing order, this one is moving down in decreasing order. For instance, when they designed Abuja, listen very well, sirs. They designed Abuja for 1 million inhabitants. That was the original design for Abuja in 1978 in Wiesbaden, Germany. That's where the design took place. That's the headquarters of Julius Berger, or Befinger Berger, the mother company of Julius Berger. The model, the design of, they combined the model, the city of Frankfurt and the city of Curitiba in Brazil. These are the two models that they design Abuja. Any of you that have been to Germany, the day you go to Frankfurt, you feel like you're in Abuja. In fact, most German cities is just like, when I'm talking about Abuja, gentlemen, I'm talking about central area, I will say, I'm not talking about, please. Those are satellite towns. Wike is trying to make things better now, okay? Because a lot of abuse is going on in satellite towns, just like in Lagos. I mean, Lagos is, you know where is Lagos. Okay, so when they designed Abuja in 1978 up to 1982. Sorry? I can't hear you, sir. Okay. Abuja is phase 1 I'm talking about, sir. And meanwhile, by the way, phase 1 is only 80% designed, not even 100%. So phase 2 is what they are trying to do now. I can see some Chinese are trying to do the water reticulation for phase 2. Phase 3, nobody's talking about that one. So phase 1, phase 2 is still what Abuja is 25% developed. So a lot still need to be done. So when they designed Abuja for 1 million inhabitants. And because they foresee that the city is going to grow very fast, they used a safety factor of 2.3. Because in water, in engineering, a lot of us know, after you have gotten your value, which is your design value, you must multiply with a safety factor. That safety factor is what takes into consideration losses, population explosion, future development, forecasting. Because if you design a city for 1,000 persons in 2025, and if that city grows to 10,000 persons in 2030, you're going to have a problem. So that is why in 2025, you know that this city is going to grow to 10,000 in 20 years. They're going to use the parameters of 20 years to design today so that development will catch up with it. Please take note, this is very, very strategic and very, very important. Let it be one of your takeaway for today. You must forecast very well. And most times, what you use to build in that parameter is what we call safety factor. Once you mention safety factor, it's an accumulation of many things. It's an accumulation of oversizing, undersizing, future development, change in lifestyle, anticipated water losses, anticipated population explosion, anticipated design error. So factor of safety can comprise 5 parameters. This is where engineers hide their error. Or where we say, sorry, that's the wrong word, where engineers hide their uncertainty. Because engineering is a science of approximation. Okay. So here, back again to water demand requirements. Whether you're designing for a hospital, you're designing for schools, you're designing for administration, you're designing for hotel, you're designing for agricultural farms, or you're designing for commercial areas, there are different parameters you have to use. There are different water requirements. For instance, in hospitals, the water requirements on the average is 340 liters per patient per day, though it can range between 120 liters to 800 liters. In a good functional hospital, you need a lot of water. That's by the way. And you can use a factor of safety of 1.3 or to 2.3 for the hourly and for the daily. Remember what I said before. If you are designing your tank is designed based on daily flow. If you are designing your transmission from water source to storage tank, you design it based on daily flow. But if you are designing your distribution network, you design it based on hourly flow. Let me say it again. If you are designing your distribution comprises 3 tiers of pipes: your primary pipe, your secondary pipe, and your tertiary pipes. The primary pipe, some people call it main pipe. Main pipe is the one that brings water into the system. It must be biggest pipe. If you get it wrong, every other thing goes wrong. It's the key major design. In fact, if you get your primary pipe right, you don't need to worry about secondary and tertiary. Because if there's error in those ones, other areas will work. But the primary pipe, if you under-designed it, you have issue. Water will not even flow. And it can be very catastrophic. And that's why, as I say, water engineer, you have to know this course. You need to understand this principle. And that's why you are here. Because I've seen where they lost a lot of millions. I want you to imagine, gentlemen, where you lay a 6-inch pipe 2 meters below the ground, and suddenly the water is not flowing. Are you going to retrieve that pipe? You can't retrieve it, sir. If it's a PVC pipe, it's gone. So that's why you have to be careful before we lay any pipe inside the ground. Because any error in calculation, it is going to be cost tsunami. It's going to be a cost tsunami for you. So for schools, watch this. They require just 6 liters per pupil or teacher per day. 6 liters. And there's no specific range. 6 liters. Because pupils, it's just for them to go to toilets, and maybe drink water. That's all. So, but then when you go to hotels, they can use as big as 290 liters per capita per day, per person per day, or per guest, as they put it here. 290 liters per guest per day. Remember, 1,000 liters is 1 cubic meter. That's why I'm ignoring this cubic meter. 1,000 liters is 1 cubic meter. And the range is between 100 and 140 per guest. Okay? Then, as per room, You know why they put room differently? Because some room can be deluxe room, family room, presidential suite, and what have you. So it can also be standard room anyway. That does not require much water. So it can also be between 70 and 140 liters. So these are range. So when you're doing your calculation, the good thing is that all these things are standard. So if you go online and type it will give you like 1,000 standard samples. So you don't need to worry yourself about this. Now, if you are also designing for pumps, motors, mechanical equipment, you should know that they will last for between 5 to 10 years. If you are designing for wells, buildings, treatment plants, they're not going to last forever. They will last for 10 to 15 years. So you should factor in those things. It's very key, especially in your cost analysis. If you are designing water towers, long distance pipelines, distribution network, you should design between 15 to 30 years. In other words, don't go beyond 30 years and don't go less than 15 years. If you are designing dams, storage reservoir, you should be factoring them, putting a safety factor that will take care of them in the next 30 to 40 years. Also, in forecasting, you should make use of arithmetic progressions. You should you should develop look for formulas that will forecast your population. Population of Nigeria is projected to be so years. The population of these areas, based on say is the university, is this, is that, is going to be so thing. You look at the growth rates, you use the appropriate parameter to forecast. Okay. So that's the end of that. Any question? So we go to chapter 4. Chapter 4 will be the supply system. So general aspect of selection. I mean, I read this and understand. Huh? I'm not going to go into all this. So for want of time. So let me just give us an idea here. So there are two systems of water supply systems, the gravity system and the pressure systems. Well, let me tell us that 90% of water systems in the world is gravity systems. Take note of that. Normally, it is designed by gravity. What is designed by gravity? Here you have the water source. From the water source, you go to the treatment plant. From treatment plant, it goes to your pumping station. The pumping station pumps the water and it pumps it into a storage reservoir. Most times, the storage reservoir is located at the highest point, the highest elevation, the highest point in the community, the highest point in the layout is where your storage tank should be located if you are designing a gravity-based system. Normally, your water source will be at the lowest level because water flows at the lowest level. I understand. And sometimes also groundwater before you now pump it to the surface. Apply some level of treatment, and then you pump it to the upper reservoir. If the whole place is a flat place, it means you need to elevate because you are designing based on gravity. And like I said, 95%, if 90% of water distribution systems, especially in energy poverty areas or energy scarce area, let me use a better word, must be based on gravity. However, in some rich neighborhood, you can also have a pressure system where you put pressure, you use pressure to pump to the last consumer. The difference is that the pressure systems consumes a lot of money.
Where you? Hello.
Then I give us an example of a typical water supply system in a city in Germany, how Germans do their water supply systems. Listen to me now. So this is what they do, basically, let me just say this. I love the country. Every community will have a company or a firm managed by a private sector and the community to supply water to that community. The community provides oversight. The company provides the water system, the pipes, the pumps, everything, and they collect the tariff. The community serves as consultants to watch what they are doing. And most times, these communities will now go to universities, recruit people from that community that are professors, that are water professionals. They become the advisors for that community because water is a social thing. So here, they have 14 communities with 120,000 inhabitants. So what they dug was 14 wells. Now, your mind should be telling you, we call it a centralized water supply system, but why are they digging 14 wells? Follow me. And they have 4 treatment plants. What I'm trying to bring out here is for you to understand that when we say centralized water supply system, there's some element of decentralization in it, but they are planned holistically. So it's more like having centralized systems in small cubicles, in small local government, in small districts, in small phases, in small subsets. So they have 4 treatment plants and they have 35 storage tanks. They have 1 water tower. That water tower is probably servicing some people that have issue of head. I'll still come to that. And they have a total of 200 kilometers of transmission pipes. And their water source is local sources and long distance water supply. Probably local sources is not enough. So they now augmented it with long distance water supply from other cities, other communities. The Lower Usman Dam in Abuja cannot service Abuja because it is 100 cubic meter reservoir. But few kilometers away is a big dam in Niger State called the Gurara Dam. If you are flying in from Abuja, you see it from the sky. The Gurara Dam has a capacity of 900 million cubic meters. Remember, Lower Usman Dam, which is the only dam in Abuja, by the way, water, is 100. So Gurara Dam is 9 times bigger than Lower Usman Dam. When El Rufai was the FCT minister, El Rufai dug a 3-meter pipe, concrete pipe, from Lower Usman Dam in Abuja to Gurara Dam in Niger State, with locks, with all safety features, because that is not small water. When they open it, can cause havoc. Water hammers, hydraulic jumps, and what have you. It will be so massive. But they know how they calibrated it. They know how they build water blocks. What do you call it again? I'll get the name. Pressure blocks here and there. So each time there's no water in Abuja reservoir, what they'll do, they'll open that 3-meter pipe and water will rush from Lower Usman Dam and fill up the dam in Abuja. That is why most people that live in phase 1 of Abuja, they don't lack water. If there's one thing I know of Abuja water supply system, is they can be trusted. And to further put what I'm saying, if you go to Lower Usman Dam, they have 3 phases of water treatment. They have phase 1, they have phase 2, they have phase 3. So that at every point, they have enough water to service Abuja. Gentlemen, for crying out loud, this is the capital city of the country. So it shouldn't be a big deal for them to do. And Abuja has 6 tanks, 6 big tanks, which is grossly inadequate. Abuja was designed to have 10 tanks. So far, they are number 6. They are built like 4. The tanks surround the city. So from Lower Usman Dam, they will pump water to the tanks. From the tanks, water will supply to the city. Phase 1, anyway. When we say Abuja phase 1, for those who live in Abuja, who know Abuja, phase 1 is Nnamdi Azikiwe Road to Maitama to Asokoro. I don't know if I should show us the map of Abuja. Maybe after the class, I'll show us. So we're talking about phase 1. We're talking about from Pape Junction. That road from Pape Junction to Bega, to Area 1, to Area 3, to Apo Bridge, the new Apo Bridge. That is, then move backward towards Guzape and then State House. That is Area 1. So that's comprised of Garki, Wuse, Maitama, Asokoro. So they have about 4 tanks. So once water comes from those tanks, and those tanks are located in the highest points, so that water can flow through gravity. So this wells. So if you look at it, you know that each well is dedicated to each community. So once they pump the water, they pump it to the 35 storage tanks. That means averagely about 2 tanks per community, or some 3. And those who don't require tank, who need something more than tank, they provided water tower, which could be like a elevated tank for us here in Nigeria. So that is that. It's a very good case study to understand how these things work. Then there's another one in Baden-Württemberg from long distance water supply. Those ones, they don't have dams, they don't have these things. All they just do is they take water from the lake. So they have 1 lake, they have 1 treatment plant, and they have 320 communities with more than 4 million inhabitants. The daily peak flow of water is 360 liters per day. And at peak period, it's about 531. If we divide 531 by 360, it will give you the safety factor they used. They have about 39 storage tanks distributed all around the communities. If you look at it again, you'll find out that it's almost 1 community, 10 communities, 1 storage tanks, about that. And the tank has 471 cubic meter of storage, servicing 4 million people. You can do the maths. You begin to see that these tanks probably are recharged twice per day or once per day. They have 1 resource, and they have 1,700 kilometers of transmission pipelines. This is the second case, the second example of how this community. So on the map, you can see their lake, and then you can see how they pipe it, their water all around the community. So the third one is the California project. I have been to Los Angeles, yes. But I meant to understand that they take water from the Gulf of Mexico and they transmit the water untreated for a very long way using something that looks like a trapezoidal channel. I think I've seen it online. That these days they are trying to build solar panel on top of it to minimize water losses due to evaporation. So they use something like a trapezoidal system to transmit water from the Gulf of Mexico to inland into California, because California is a water scarce city in America. They keep looking for ways to augment their water because of the arid nature of some of the areas in California. So it's also a case study that can be studied. Maybe after the class, you can look it up online and learn 1 or 2 things about it. Just type in California Water Project. Okay, it seems we are done with this. And that's chapter 4. right? So we'll go to chapter 5. Some of the chapters have nothing inside them. Planning process. So let's look at the planning process. Okay, so basically in design, you do primary design and you do your final design. Then your essence of your design is to supply all consumers everywhere with the drinking water of sufficient quality, quantity, and pressure. So 3 parameters: quality as a water expert, as a water consultant. You supply water in terms of the quality, in terms of the quantity, and with the right pressure. Then you safeguard your supply by making sure you have a protected source, use a gravity systems, and we advise you use a loop system. We have 2 systems in water design distribution network. We have a branch system and we have a loop system. You also try to minimize risk by following the following advice. Make sure your source is protected. I can't overemphasize protecting your source. Make sure it's away from mining activities, it's away from sewage activities, it's away from all kind of contamination, anthropogenic contamination. Then disinfection. Then ensure 24-hour supply. Mind the distance between your pipe network and sewer. Very, very important to avoid contamination. And make sure your system is tight and secured. So, you can read all this one, understand. So minimize your pumping cost, minimize your treatment cost, minimize the number of pressure zones. We'll come to that. And then minimize the length of pipes by looping them. I've said it before, you need to choose your systems, either a pump system or a gravity systems. For your tanking, you need to know where to station your pumping station. Your storage tank should be elevated if you need more pressure. You can use your branch systems, you can use your loop systems, and so many other things to look out for. We're done with that. We go to chapter 6. We are getting close to chapter 8 and chapter 9, which we'll dwell on more next week. So, like I said, I've emphasized this. 2 systems, the gravity systems and the gravity system and the pressure systems. This place will explain to you, when we talk about, the first thing I said, who are the mechanical engineers and who are the civil engineers? Because water is a domain, is a multidisciplinary group for water engineers and for mechanical engineers and for civil engineers. These are the 2 professions that hold the water domain very, very well. So for those who are civil, it will be good for you to study about pumps. You know 1 or 2 things about pumps, so that you don't leave it all for the mechanical engineers. So somebody says you cannot connect. These sections will be recorded. Okay, now you look at the pump. So this is a typical centrifugal pump. Mechanical engineers know much about this. So the pumpers are the pillars, the shaft, the casing, and everything, just for you to understand how they work. Okay, it's more like take water and then with the centrifuge systems push it to a higher pressure. Then this is other types of centrifugal pumps. It can be horizontal, it can be multi-stage, single stage, can be multi-stage. Take water, pump it, give it more pressure. Then it can also be submersible pumps, which can be used in borehole. It still work like with centrifugal technology. Then factors that determine pump, the speed of pump. This will be boring for mechanical engineers, but for civil engineers, just find time and go through all this and learn some things. So when we talk about laws for hydraulics, for pumping design, the head of a place is made up of 3 heads. It's made up of what we call the geodetic head. You have head losses due to friction and head losses due to velocity. That's why when you want to measure the hydrostatic head of a place, it is not only the difference in elevation. You need to factor in the head losses due to friction. Friction because that water is going to move on a horizontal pipes. Pipes have limitations to flow. So you need to consider that. Then when water is moving inside the pipe, the water has some level of turbulence. What do you call it again? Momentum. So there's also pressure loss due to momentum. If you can go back to our early years in engineering, you know all those things. So at the end of the day, your head loss comprises of your geodetic head loss and your frictional head loss. So to determine the power requirement of a pump, is simply that head loss multiplied by the discharge, multiplied by a factor, divided by the efficiency. So if I know the quantity of water I want to pump, I know the head, then I can determine the kilowatts of pump required. That is what this place is talking about. So pump curve, we'll come to all this when we come to the software application, but then to size any pump, you need two key parameters: the discharge, the frictional loss, and the head. So pump can be operating point of a pump. When we read all this, we understand them. So when you have two pumps, if you double two pumps, if you connect pumps, you can connect pumps in series or in parallel. When pumps are connected in parallels, the head is the same. The Q, the discharge will increase. I say it again. If you connect two pumps in parallel, the head remains constant, but the discharge increases. Okay. Then, if you connect pump in series, the discharge remains the same, but the head increases. So what it means is that if I'm looking for head, what do I do? I connect my pumps in series. If I'm looking for discharge, I'll connect two pumps in parallel. Please, I want that to sink in. I want that to sink in. It's just like Kirchhoff's law. All the laws in engineering, I love engineering. Once you master one law, you apply it to other laws. Very unique. So here, it's also about pumping. I'll still come to that later. So basically, sometimes you configure your pumps to flow at different frequency, different rates. So all you need to do is to look at the pumps and you check the parameters. This is a very simple thing. It's not a hard thing. So let's go to chapter 7. We're coming close gradually, also heading to the end of today, which is more like a foundation. Then, but during the week, I will give us one or two things to do to help our progress for next week, 2 hours next week. Functions of elevated storage tanks. Storage tanks are to equalize the difference between the inflow and actual demand. This is very key. Let me ask us, why is it that you pump water from your borehole? You don't go straight to your tap, no? You need an elevated tank. Why? Because you want to equalize the inflow. Because it's not the rate at which the pump is pumping from the borehole you are consuming. So you need something to equalize that flow. And that is what storage tank does. The second thing is to provide water and pressure in case of a breakdown. In this case, not even a breakdown. Your pump does not work all throughout. You can pump water for 1 hour per day or 2 hours per day, and then you pump the next day. So during those period of non-pumping, you need a water source. Also, it helps to provide constant pressure. If your elevated tank is, let's say, 6 meters, that will be giving you about 0.6 bars. Okay, 0.6 bars. So it means all through your building, you are sure of 0.6 bars all through the building. So that's not a problem for you. You get the point? Then, in case of fire, you have water source. So we say that the tank can be surface, underground, and elevated. If you put your tank on the surface, it means you need another stage of pumping. For instance, in where I stay, in my house, I have 2 pumps, and I have a surface tank. The surface tank is because I treat water. The water source is not too good. So we pump water from the well because it has high turbidity, high iron content. So pump it to the surface tank. And when it settles, it gets aerated, maybe for 12 hours or so, settles down. The TDS, the total dissolved solid, goes down. Then we now pump it to the upper storage tank through a filter system anyway. So that is that. So here, we have what we call counter tank. Sometimes the pressure, the location of the tank might be higher in pressure. Normally in your network, we don't advise you to have more than 8 bars. Let me say it again. The maximum pressure in your network should not be more than 8 bars. Recall that the product you have in the market, most of the pipe you have in the market, some of them are even 6 bars, especially the sewage pipes. Most of them are 8 bars, some of them are 10 bars. Only in exceptional cases we are seeing 12 bars, because the higher the bar, the higher the cost. So this PPR pipe, this green pipe we're using, I think it's about 10 bars. 10, sometimes are 10, some are 12. So it is now advised that don't exceed 8 bars. Because if you exceed 8 bars, you know what the problem, it will burst or it will have issues, it will have leakages. However, in some instances, you can find out that your tank is in a place higher than 8 bars. In that case, you bring in what we call counter tank or buffer tanks. The buffer tanks or the counter tanks are just meant to cause the pressure, because the pressure is at a higher elevation. Hence, you need to cut it down a little bit. Okay, sorry for small break in transmission. So we have the flow-through tank, we have the counter tank. The importance of counter tank is to control the pressure, which is very important. So once you find out that the pressure is going beyond what you expected, you put a counter tank so that the counter tank will break the pressure before it gets to your tap. So here we have what we call service pressure. When we are talking about service pressure, something like for each story building, each story building is about 3 meters, okay, headroom. For each story building, you need a service pressure of 5. The minimum service pressure in your system should be 20 meters of cubic meter of water. In other words, all we are saying in essence is that the minimum pressure in your network should be 2. Remember, I said the maximum should be what? 8. So the minimum should be 2. On a standard scale, you can have 1, you can have 0.5. It's okay. It simply means your water will not run at the required pressure. Many of us will remember, some of us who you live in upstairs, okay, if the pressure is not good, if you on your tap, water will be drizzling. That is not what it wants to be. Compare it when you go to abroad or you go to London or you go to UK or all these places. Once you on the tap, you will see what is called pressure. Okay, so the minimum pressure in your system should be 2 bars. So that 2 bars is like 20 cubic meters of water. And that's what you're seeing here. So as you are going up, so for instance, this is like for a 1-story building, you provide 22 bars. It means if I'm going for a 2-story building, I will provide 25 because I'm going to lose 5 and maintain minimum of 20. If I'm going for 25 for a 3-story building, I'll provide for 30. Those of you who are consultants, this is very important for you. If I'm going for a 4-story building, I'll provide for 35. What it means is this: if you are designing for a water system, you must ask the architects, how many floors are we expecting in this area? You must ask that. Your design will focus on the highest floor. Let me say it again. You must know the highest number of flow. You don't use the pressure at the tap at the ground floor for your design. You use the tap level at the highest floor, or the highest person you are designing for, or the location of the highest person. In other words, if I come to a system and somebody is at elevation 300 and somebody is at elevation 320, my design will focus on the person at elevation 320. That means my tank will be at elevation 350, let's say, or elevation 340, so that I will supply maximum pressure requirement to the person at 350, at 320. The person at 300 will already get water because the person is already 220 meters below the person at 320. So if the person at 320 will get water, it simply means the person at 300 will also get water, but at a higher pressure. I wish I can demonstrate this with with the whiteboard. I don't know. Let me see if I see whiteboard here. Hope it doesn't stop my whiteboard. Or let me whiteboard. Is it a whiteboard? No whiteboard in Zoom again. I'm sorry. No longer have whiteboard. But I would have showed us something. Huh? I don't have a whiteboard. Sorry, gentlemen. So, for instance, how do I demonstrate this? If somebody is at this elevation, okay, and another person at this elevation, then it means my tank should be at this elevation. So let's assume now that this place is 340 meters above sea level, and this place is at 320, and this person is at 300. Okay, it means once water flows from here to here, I will have a head of 20. I have my required 20 service pressure. Hold on, sorry. It means I have my 20, my service pressure. I meet up with my service pressure. Okay, then the water now flows from here again to here. What's happening? This is draw. It means service pressure here will be what? 40. And the service pressure here will be what? 20. So you see, my focus will be on this person at 20, though he will be getting at the base pressure, which is 2 bars, no problem. This person will be getting water at 4 bars, normal. Besides, why? Because the maximum pressure within the system is still within 8 bars, which is the maximum required to ensure sustainable design. Now, even at 5 floors, 5-story building, you see that I'm still supplying the person at 40. It is when this thing is getting to maybe 12-story building, I will now thought of bringing in a new tank on a new level. So the maximum service pressure in your network should be 80, and the minimum pressure should be what? 20. Just take note of that. We'll come to the design, you understand all these things. So for every floor, I will just add 5. I think that's well understood. Okay, so but now the pressure of a zone, or the pressure that a zone will now have will now be the maximum service pressure minus the minimum service pressure minus the pressure of the reservoir minus the pressure losses due to friction. Don't worry about all this. You will understand it better when we come next week on in calculation. We're just laying a foundation. Then for the volume of your storage tank, the volume of your storage tank is 3 parameters: equalizing volume, firefighting, and emergency volume. Okay, equalizing volume, firefighting volume, and equalizing volume. Then that is what makes up your. So if you are designing for your tank, storage tank, you must know, in addition to the equalizing volume, which we have discussed, you must provide some firefighting in case there's fire. That water cannot be used. Some people call it dead volume, but the technical word is fire volume and emergency. There are sometimes you need emergency volume. You on it. I will explain. Then I've explained this before. So this has to do with water consumption. So water consumption pattern, I've explained it earlier on in this test. And then this is the water consumption pattern, how to get your equalizing volume. I don't know if I'm comfortable to do calculation today, because some of us are already exhausted. But let me just finish with this. So here is telling you, just like I explained, that your tank, how you have a tank, is to store excess volume or to equalize your volume of usage. So here now, the blue line represents the water flowing into the tank on a constant 24 hours note. The green one shows how water is being consumed. For instance, you can see that between 0 hours and 4 in the morning, or 4 hours, the water consumption is low. Then towards 8, 9, or 8 o'clock, the water consumption goes high. Then the water consumption remains a bit constant until around 8 p.m. in the evening. The water consumption goes high. Now, if you check, you see there's a gap between the blue line and the green line. That shows you the volume of water that should be stored. Sometimes you find out that during the morning hour until around 12 o'clock, the consumption is lower than the inflow. But towards the night time, you find out that the consumption becomes higher than the inflow. So it means the excess water that you have stored in the morning will not be used in the evening. This is for 8 hours pumping. If you're pumping for 8 hours and you have a good tank, okay, meanwhile here, this thing now shows you that the tank you require for this system is just 50. Because most times you see people having bigger tank that they don't require. So doing your consumption pattern will help you know the minimum tank requirement you use. In this case, because we are pumping for 8 hours only, we require about 170 liters of tank for storage. You know, what this thing shows is that when you are pumping water within morning to 8 o'clock, you have more than 200 liters of water. Whereas, meanwhile, what you need for your consumption is just maximum of 30. It means the excess 170 need to be stored somewhere, and that is stored in your storage tank. In this case, we are pumping for only 8 hours, and that 8 hours is between 8 o'clock and 4 o'clock. It means you need about 100 liters of water as against 170. In other words, you're not pumping in the morning hours where you don't need too much water. You start pumping water around 8 in the morning and stop around. So the capacity of the tank that you need in this case will be lower than when you are pumping in the morning. So this is also give you an idea of the best time to pump water. That means the best time to pump water, the 24-hour scheme, where there's a constant demand, not too constant demand. It means you need to pump water from between 8 and between 4 o'clock. That is the best time to pump the water. Because in the morning hours, you don't need. And with this, it means the size of tank you need will be minimized, will be optimized. Almost of these things, when we read them, we understand them. Okay, I've explained this one before. You zone. When you find out that you cannot supply water from one water source, then you split into zones. Very, very important. When you find out that the distance between your water source and the last building in the estate or in the district will lead to zero pressure, then you fragment or you do your design based on zoning. You do what we call zoning. Zone 1, zone 2, zone 3. These zones are based on the pressure, because the key thing you need in your water system is pressure. If there's no pressure, water will not flow, gentlemen. So one of the most important parameters is not even quantity, it's the pressure, because you might have the quantity, but you don't have the pressure or the force to push the water, or for the water to flow well at the consumer pipe. So in this case, you need to split this water into different zones. And that's why we have zone 1, zone 2, zone 3. So you position the water system, the wells, where they optimize the zoning formula. Because when you come to a system or a vicinity, a place like Plateau State, where you have different people are living in mountainous places, elevation, you need to allocate your tank, size your tank, allocate your tank such a way that building within a certain pressure that share the same pressure will use a particular tank. So you can have upper pressure area, lower pressure area, medium pressure area, or you simply name them tank 1, tank 2, tank 3, tank 4. Those tanks are servicing houses within a specific confined, bounded zone. You can say from zone 40 to zone 50, which is 4 to 5 head bars, sorry. You can say zone 2 to zone 4, which means houses that will take pressure between 2 bars and 4 bars. You put them together, prevent them with tank. Then those at the upper end of the estate or district, you put them together, provide them one particular tank, and they form the same zone. So you can have multiple zones. This is very key for consultants. So that when client is saying, I want one tank, you tell them, okay, no, one tank will not work. You need 2 tanks, you need 3 tanks, and these are how these tanks will be spaced based on the survey plan, based on the layout, based on the financial planning, and whatever parameters you use to discretize the zones. So construction of a surface water tank. I'll leave this for you to study it. This is the elevation, how it looks like. You know, these are cubicles. Remember, don't always build big tanks to have one baffle wall or one cubicle. The pressure or hydraulic jump can cause a problem. Even the tanks, the trucks that supply fuel tanks, if you go inside them, you find out that they partition them into tanks. It is the same principle. Water hammer can be destructive. Yes, can be very, very destructive. Avoid it. Always have dissipators. Good. So this is another design. Just study it at your free time. Depending on the layout, depending on the location, you should be able to come up with a customized solution. In the Arab world, of course, we know they build things like this, both for aesthetics and for they have money to build this thing. So these things can be very, very expensive. Okay, that's the end of chapter 7. So we now move to the big man, chapter 8. And no, let's do chapter 9. So I will leave chapter 8 out. And 9 should be like summary. So chapter 9 is summary of what we have done so far.
Sorry to cut you, sir. We can only see the top left corner of your screen.
Left corner. Can you see it now?
Oh, we can't see the full screen. It's just the top left corner.
And unfortunately, you didn't see it all this while. I went and changed the mode. I've replaced it now. Yeah. Should be showing well now. Okay. Wait. Sorry. Should be okay now.
Yes.
Okay, so I skipped chapter 8 because we are dealing chapter 8 next week, which is the formal design. So I'm just trying to use chapter 9 to check if there's anything serious. So chapter 9 is telling us about this is a branch system distribution. Okay, this is a branch system, and this is a loop system. This is a loop system. This is a branch system. Okay, so there are 2 systems of this thing. Then this one, I want you to take note of this. I think I was in South Africa recently and I saw something like this. I saw where this thing is, and I discovered that these places they have this thing. They put valves, and the valves were leaking. Actually, I went to a groundwater treatment plant. You won't believe it. You know, South Africa is a mining country. So they've somewhat advanced that after 100 years of mining activity, their groundwater is so contaminated that they are treating them now. So you can see that when they run this pipe like this, you see all these places you have these inflations. They're supposed to be air release valves. Very, very important, air release valves. Then the lower part, you need to have drain valves so that they will be releasing pressure, because if not, these places will break. I think they're having that problem in Abuja. Though the Abuja own it because of the kind of materials they use. The material they use is not PVC and is inelastic. So the pressure keep breaking them at those inflation points. So this is giving us the idea of where to provide valves, some pressure release valves, very, very important. Because pressure will build up there. Air pressures will build up there. Bubbles. They need to be released to keep the system safe. So I've explained this before. These are the lifespan of different materials you can use. Okay. If you can use steel, this is the lifespan. PVC can last, can withstand 110 bars. It can last for 25 years. Please, asbestos can last for 30 years, but nobody uses asbestos again because of carcinogenic risk. Then you have cast iron. You have the lined and unlined. Cast iron can last for 100 years, but they need to be lined. They can take pressure as much as 25 bars. You have steel. Wow, steel is the highest. Steel can take 100 bars, but they will last for 30 to 40 years. So please find time and study this. Then for hydraulic calculations, just I've explained this before verbally. You need to understand hydraulic grade lines, so that you calculate your losses very well. You can study this about Bernoulli energy balance. Sum total of energy losses must be equal to the total energy. At this our level, we don't need to go into mathematics again. Charts will take care of this. So that's why I'm not emphasizing on them. So these are the frictional frequency of different pipes we use. This is advisory. For transmission pipe, they're advising you to use coefficient of roughness between 0.1 and 0.25. Remember, coefficient of roughness is the degree of friction in the pipe. So the smoother the pipe, the lower the coefficient. So this is for economic design. If you don't want to go into any calculation, 6 meter, if the flow rate is 6 liters per second, you need 100 mm pipe, and your velocity should be 0.8. I will explain all this next week. I'm trying to make sure we end by 12, right? Let's make it a standard so that nobody comes late subsequently. So based on the flow rate you found out in your pipe, you can just use the economic design. So please take note of this, study this. Those of us that are all of us are engineers. We always have what we call economic design. Those of you that are civil engineers, when we design our design, reinforced concrete, sometimes you just go for economic design, not to bother yourself. Once I see that this beam is 5 meters span, I will say provide 3Y16, bottom and top. Once I see that this span of slab does not exceed 30 square meters, I will say provide reinforced Y12 at 150 by 150 spacing. We are fond of it. So the same thing applies to water design. Sometimes you don't need to crack your head. You just check what's the flow rate I got. This is the minimum pipe design. And most times it works. It works. That's why some designers will go and put 50 mm pipe everywhere. After this lesson, those of you that are consultants, you need to change your design parameters. Because when I see many designs, I will see uniform pipe. It's not possible. Because the flows are not the same. As your water is moving downstream, the pipe size will reduce. As it's moving upstream, it's having more load. The pipe size will increase. So this uniformity of pipes is bad design. Okay, so the same thing applies to the head losses. So all this, we'll treat them by next week. Okay, so it's because about the head. You can study this. These are from monogram. I think you want to use calculation, but for the purpose of this class, we are using charts. So don't crack your head about mathematics formulas. We'll get it done. All right. At this point, this is the end of the class. So I'll stop recording.